Hey everyone, welcome back. In today's video, we're continuing our discussion of velocity. Hello. And we're going to be adding to it transport theorem. So let's look at an example. Let's say that we have the pendulum and the groove has been cut into the pendulum, and we're looking at an object that is translating in the groove of the pendulum, and the pendulum itself is also rotating. If point N was here and we're looking at, let's say, point A, we could have a position vector P into A that is Q, X at A, and as we saw in previous video, we can take the derivative of this position vector and we can get the velocity. So the velocity of point A is ddt of the position vector. So that is ddt of q x hat A. So what happens when we take ddt of q x hat A? We're going to do product rule. So there'll be an expansion ddt of the first part, q dot, times x hat A. And then we saw this last time. The second half of the product rule expansion is q times ddt of xa. All right. So what we did last time is we took the definition of xa from the rotations and we rewrote this and we said that ddt of xa, so specifically replacing this part with ddt of cosine theta, theta 1, theta, it's fine, times xn sine theta yn. All right. And in so doing, we take it, we put it here. We can see that if we distribute the ddt, we end up with cosine to negative sine, sine to cosine, and then there's also the chain rule. Now, this process can be done for any linkage. If, suppose, we were working with a different system and we were doing some position vector to B, and let's say that we went first into A and then A to B, all right? And this was, we want VB now, so ddt. And these position vectors, let's say that those are L1, XA, and L2, XB. So in this case, we have no distance changing, but we have two different frames. So a system like this, we have N to A to B, and there is the A frame, and there is the B frame. All right. What's going to happen when you do ddt on this? Well, the ddt is a linear operator. We can distribute it to these two. We see that these L1 and L2, these are constants, the lengths. So this VB will get L1 ddt of x hat A, and L2 ddt of x hat B. So this situation where we have to take ddt of a moving frame is not going away. And the bigger your system gets, the more of these terms you're going to have included. We would like to have some compact way of resolving ddt of a frame without relying on converting it into the end frame. Consider, we've talked a few times about doing relative angles. So imagine that you defined in this system the rotation from N to A, and then we define the rotation from A to B. If, in this declaration, if we wanted to take XB and put it in the end frame, we would first have to convert it into the A frame, and then from the A frame into the end frame. So that would take both angles, theta 1 and theta 2. So if you're using relative angles, this process gets more complex, or more complicated, right? There's just more steps you have to take. The more frames that you have, C frame, well, you'd have to take C into B and B into A and then A into N, etc. So that's where transport theorem comes in. Transport theorem allows us to take the derivative of a frame. So, for example, doing this, or doing a more complicated one, further down the kinematic chain, we can take the derivative of these moving frames without rotating them, without having to manually replace them and then go through all of this algebra. I'm not going to derive the transport theorem in this video. I'm going to cut to the end. I'm going to show you what the theorem is, and I'm going to show you how to use it. So here's the claim. The claim with transport theorem is that anytime you see something that looks like this, anytime you see ddt of a frame, and it honestly doesn't have to be a moving frame. We could apply transport theorem to a non-moving frame and you get zero anyway. But anytime you see this, ddt of this frame, we can replace this. So if I have ddt of x hat a, what I'm going to do, or let me actually back up so we can see an example of it. So let's say P and A is L x hat A, and VA then is going to be L ddt x A. And you can see I've taken ddt of the whole thing, I did product rule expansion, and ddt of the L is equal to 0 because it's a constant, and we're left with this term, so ddt of the x hat A. So what we're going to do is we're going to take this expression and we're going to replace it. I'm going to say that VA is equal to omega into A, and I'm going to explain why all these parts in just a moment. And then this is cross L x hat A. So this is transport theorem being used. Okay, so this is it in practice. So we had this term, and we're going to replace it with this term. Here's where these pieces come from. So first of all, what frame are you taking the derivative of? In this case, we're taking the derivative of the A frame. Therefore, when I write angular velocity, I do it from N, and it's always from N, to A. And we're going to do some examples where we take derivatives of other frames, so we can see that in practice, but N to A. Next, angular velocity cross, so this is a cross product operator. There's many ways to resolve the cross product. I'm not going to tell you which way to do it, but however you want to solve the cross product, be my guest. But recall that the output of a cross product is also a vector. So the vector of velocity is the angular velocity vector cross. And then notice that what I have written here was this position vector. It was the quantity that we were originally taking the derivative of that yielded this ddt of x hat a term. And you literally just take that quantity and copy it down. As we're going to see with acceleration, we need to come back and eventually we're going to take derivatives of these velocity terms. And sometimes then, if you're applying transport theorem there, it's going to be angular velocity cross whatever quantity you were taking the derivative of. So we'll see that in practice when we get further in. Let's do another example. All right, this time, let's say that P in B is equal to L1 x hat A plus Q x hat B. Now, we don't have a diagram drawn for this problem, but this is a valid position vector, and at this point, I feel like we understand this is a constant, this is a variable, and these are two rotating frames. VB then. VB is ddt of all of this. So what do what do we do? Well, we can distribute the DDT. So I'm going to parentheses here plus DDT. All right. We can do a product rule expansion. If we do a product rule expansion on the first term, then that first term in that first expansion is going to be DDT of L1, and that's 0. And then we'll be left with the second piece. So VB is going to be L1 DDT XA plus, and we know what's going to happen when we do a product rule expansion on this. That's the translating and rotating at the same time. So we'll have DDT of the scalar Q, which we can do very quickly, and then Q DDT of X B. Okay, we have two of them now. I have DDT of A and I have DDT of B. So twice now, 2 points in this problem, can we use transport theorem? So VB is going to equal this first piece. We can do transport theorem on this piece. We're taking DDT of the A frame, X hat A. So it is omega into A. We're going to do a cross product, and I need to fill this space with something. What am I taking DDT of? This X hat A, but where did this come from? This came from taking DDT of this position vector. Take this position vector and bring it down, L1 XA. Okay. So this became this. Next, Q dot X hat A, we don't have to do anything with that. It's already resolved. We can bring that straight down. And then this piece, we can do transport theorem again. So I'm going to say omega, this time, what are we taking DDT of? The B frame. This is omega in to B. Now, comment. It doesn't matter how you define the B frame here. It doesn't matter if you're doing absolute angles or if you're doing relative angles. When you apply transport theorem, it is the total angular velocity from the end frame all the way down to that rotating body frame. So it's omega into B, cross, and then we have to bring in a vector here. What do we bring in? It came from this. Where did this come from? You're taking DDT of this position vector, take that and bring it down. Q, X, B. These are equivalence expressions. And this is also how I am going to solve DDT, how I'm going to take care of these DDT of moving frames from now on. So the long method that I did in the previous video, I'm not going to do it again. If you want to do it on a homework or an exam, be my guest. Okay, so now that I've done this, what does it actually mean? What do we do with this stuff? Well, if you want to resolve these cross products, we have to know what these angular velocities are, right? So let's do an easy example using absolute angles, and let's say that our angular velocities have been defined this way. Okay. So what we're really looking at here is we're looking at two rotating bodies, and on the second body there's a moving point. So it's effectively this. We have, here's the first link A with the A frame attached. And then in this second link, we have some body that can translate, something like that. And we're keeping track of a translating point, being tracked by Q. All right, so again, I recommend you do angular velocities first. I think they're easy. You can do them from observation. Here's A frame, it rotates with theta 1. Here's B frame, it rotates with theta 2. And since in this problem, you can see how we define them, going from N to B is only the angle theta 2, that means this is an absolute angle. Okay, so we have to take care of these cross products. All right. All kinds of ways you can solve the cross product. I'm going to do one of them here, and this is actually not the way I like to do it, but it's usually the way that my students know how. So you have 3 columns, and I usually just call them 1, 2, 3. You'll see some people write X, Y, Z here. It doesn't matter, it's the same thing. So 1, 2, 3, we have 2 vectors being crossed. There's an angular velocity and there's a position vector. So you take the first one and you put it in the first row, and you take the second one, you put it in the second row. So omega into A, we have to load it into this first row. Omega into A, I've got it written right here. What are the dimensions of omega into A? This is a 3 by 1 position vector. These omegas are 3 by 1s. And you can think about them if you need to, like this. We could say omega into A. I can write it as a vector, and it's 0, 0, theta 1 dot. So it's a theta 1 dot in the Z direction, and there's nothing in the X and Y's. So I'm going to take omega into A, I'm going to put it right here, and it's 0, 0, theta 1 dot, and then we take the position vector. The position vector is L1 in the X hat A direction, and then it's 0 in the Y and 0 in the Z. So L1, 0, 0. Okay, and then from here, if this is how you like to do it, you solve for the X component by covering up the X and then doing cross multiply, positive in one direction, negative in the other, and you can see that that's all zeros. You cover up the second column, and this is now your Y solution. This time it is positive in this direction, negative in this. So if we resolve this cross product, what we're going to get is cover this up, and then it's positive L1 theta 1 dot, and that was the Y column, and these quantities are in A frame, so this is the YA direction. I'm going to bring the next one up, q dot X hat A. So that's one way to solve a cross product. How else could you do it? I've had some students do these kind of like cross diagrams, and they do some 90-degree rotation on it. That's fine as well. Here's what I prefer to do. So I can take this and I can put it in here, and this is just theta 2 dot ZB cross QXB. I prefer to just do the cross product knowing the frames. So X cross Y is Z, and Y cross Z is X, and Z cross X is Y, and if you reverse any of the directions, your answer is negative. That's it. So if you did X cross Z, for example, you get negative Y. So what do we have down here? We have, we've got theta dot around a Z, and then we're crossing a position vector in the X. So that's Z cross X. So take the scalar terms and just multiply them. So your scalar terms are Q and theta 2 dot. And then take your directions, Z cross X. Z cross X is going to be Y. So this is Y, B. Okay, so that's that is what you get when you resolve these cross product terms. You get this. Now, if you look, those two look a lot alike, don't they? Because if you recall from the last video, we said there's only 2 types of velocity you're going to get come out of this. You're going to get tangentials. There's a tangential, here's another one. And then here's a slip. So the slip arises whenever you have a translation variable. The tangentials come out of rotating bodies. So when you practice this a lot, when you start to get good at it, you can just look at a position vector. The original position vector was L1XA plus QXB. So once you get good, you look at this and you say, okay, this first term, that's a constant, that's moving. That means this is going to generate a tangential velocity. The next term, That's a variable, which means there's going to be a slip, and the B frame is rotating, which means there's going to be a tangential as well. So practice it. Eventually you'll be able to look at the position vector itself and have some expectation of what the velocity vector is going to look like. Okay, I do want to do an example while we're here. Let's do an example of relative angles. And we'll do the same problem. So we have this first joint, and all the first joint does is rotate, and then the second joint has a slot in it. And there is something in that slot that is moving, and we want to keep track of that. So there's your point B, here's your point A, here's point N. Now, strictly speaking, I would say this is actually a 3-body problem, because you have A frame and you have B frame for the rigid body, and then you would probably model this as its own body inside of that groove. So, strictly speaking, we could call it body C, right? Okay. And then B, let's put B down here on the tip. So there are the points, and then for the frames, we have XA, YA, and then XB and XC. These are the same things, and then here are the Ys. All right. Now, I say we're going to use some relative angles on this one. So what does that mean? That means for the A frame is just like we've always done, and no difference in the A frame. Theta 1, and we're going from XN to XA. So your trig expressions are the same as we've always done. From the N frame to the A frame. But for the B frame, let's define the B frame as rotating through some angle with respect to the A frame. So XN and then XB, and not XN, there we go, XA, okay. And then here's the Ys, so YA and YB. They're there as well. Angle theta 2, we're going to define the rotation now from A to B. So what happens with these trigs? We've done this once before, but this time, XB, and we bring in those same trig expressions, cosine. The angle is theta 2, and we're defining it with respect to the A frame. So plus sine theta 2 YA. And I'm just going to say dot, dot, dot. We can fill in the rest. All right, so these are the relative angles, right? Because now we're just going from the A frame to the B frame. So how does the rest of the problem now change? There's also the C frame. We could just say, I'd prefer that you not clutter up this diagram. I would prefer you do a second diagram off to the side, and you can say, hey, by the way, here's B frame and here is C frame, and they happen to be aligned. So just do a third diagram. I think that's the easiest way to do it. Okay, so you do all of this. What changes? Well, because we did relative angles, the two rotations that we defined were into A and A to B, noticeably different than into B. Before you do linear velocities, I recommend that you define your angular velocities. Because you did the rotation from into A, you define your angular velocity into A, and that was theta 1, so this is theta 1 dot, and we're rotating about ZA. Next, because we define the rotation from A to B, when we define omega, omega is from A to B. The angle is theta 2, which makes this theta 2 dot around ZB. Okay, remember when we use transport theorem, we want the total angular velocity, which means we need omega n to B, which is the linear addition of these two into A and A to B. So what is omega into B now? Well, now it's theta 1 plus theta 2 dot in the Z, and we can say ZB. So I'm able to group these together because ZA and ZB are the same thing. We just add them together. All right, so if you're using relative angle, you end up with angular velocities that look like this. So how does this affect transport theorem? It's the same position vector we were working with earlier. L XA plus Q, and let's change something up. Just for a moment, what if we had rotated this this frame? Because sometimes you're going to have to do a position vector in other directions. So what if we picked that direction as YB and also YC, C frame as well, you're there. So that would put X in this direction. So consider, we could have a position vector like this. L1x at A plus Q y hat B. That's absolutely valid. When we go to find the velocity, we're going to take ddt of this thing, as we always do. ddt of P into B. And what's going to happen? This first term, you can do product rule expansion. The L1 is a constant. So L1 ddt x hat A. You're going to take ddt of the second term. Product rule expansion. The Q is a variable and the YB. So plus Q dot YB, right? That's just bringing the scalar right down. And then plus Q ddt YB. The fact that this is YB, it doesn't change anything fundamental about the way that we approach the problem. Next, VB is equal to, we're going to take these terms and we're going to replace them with transport theorem just like we did before. Omega in A cross, bring down that original position vector, LXA. Bring down this scalar derivative, Q dot. All right, we want to do transport theorem on that term down there. We're no longer taking ddt of x. Now we're taking ddt of y. How does that change? What does it affect? We're still going to use omega. We're taking ddt of the B frame, and it's omega into B. We defined this one using relative angles. It doesn't affect this. It is still the total angular velocity of that frame. So omega into B, cross. Now, what do we bring down? We bring down this position vector, and it's a little different this time because we're defining it in the YB. That's okay. We bring this down, and now it's cross Q YB. Okay. What were these things? This was theta 1 dot ZA. This one now is theta 1 dot plus theta 2 dot ZB. Okay, VB. Multiply the scalars together, L1 theta 1 dot, and it's Z cross X, which yields positive Y. Bring down the scalar, Q dot YB. And then next, theta 1 dot plus theta 2 dot. That's a number, whatever it is, it's just a number together. These things are going to travel together. And we're going to multiply that by the scalar. So I'm going to say Q multiplied by theta 1 dot plus theta 2 dot. This time it's Z cross Y. Z cross Y. Z cross Y is negative X. And this is B frame now. It was B frame coming in on the two inputs. If you're going to do a cross product on two things, they have to be in the same frame. So ZB cross YB gives negative XB. There's your third term now. And we can look at the diagram and we can ask, does this make sense? Well, remember that the velocity of B is going to be tangent to the path. So let's say for now that theta 1 dot is equal to 0. That means this first bar is not rotating. And then we have some positive value for theta 2 dot. That means positive rotation, which means the velocity of B is in this direction, which the way we set the frames up is in the negative x. So this looks good. So that's how it changes. If you use relative angles, you end up with these more complicated angular velocities. On these two-dimensional problems, it's not necessary. I'm not going to make you do it. If this were an actual machine and you were using sensors off the joints, you'd need to do it as a way to leverage this, the data coming off of the sensor. And we are going to do a 3D problem in another video. And in 3D problems, we have to use relative angles. So we're going to see something like this crop up as well. Okay, so what's going to happen in the next couple videos? We're going to actually go through constraints again, and we're going to look at derivatives of constraints. Some of them are really easy, and some of them take a little bit. And when we do that, anytime we encounter something like this, ddt of a frame, I am going to replace it with transport theorem, and I strongly recommend that you practice that. And we're gonna, like I said, we'll do a 3D video, and then just depending on how much time we have before exam 1, maybe a couple other worked examples, etc. But so this is where we're going in the class. This is where you're going on your homework 3. So make sure you feel comfortable. If you have concerns about what I've done here today, let me or the TA know. All right, so that's it for this one. Practice this. Make sure you feel comfortable. It is important. I will see you next time. Good luck.